Okay. Okay. So once again, I welcome each and everyone to join in the technical talk present by the Indian Institute of Plant Engineers. So this talk will be in line with the World Water Day as well as plant engineers. So it is a combination of together. So it is nothing not only with water. So it always related to the plant engineers. So we have seen about the introduction about myself. I was an expert in the related to the design of centrifugal pump. So my presentation will be directed towards the centrifugal pump and then pumping system. My topic for presentation is water management through the efficient pump design. Yeah. So this is the outline of my presentation. So we'll just have a look what is pump and then various application of pump, how the pumps are classified or a group, and then what are the basic components which are there in the pump, and then various characteristics which is there for the pump, and then what are the energy consumption and pump life cycle for any pump for any particular case study. And then based on this I have made a summary and then some of the takeaway for a research on pumps, because I'm not sure about the audience. I came to know there are various participants of different categories, so I'm just given an overview what are the research can be carried out on pumps at last. Okay, now you can able to see this is nothing but the water flow diagrams as we all know. So in the world around 70% is covered by the ocean, and then the waters from the river will be tapped and then it will be treated for various applications. So you can able to see from the presentation it can be used for the indoor uses, mainly for domestic, and then commercial use for the industries and various manufacturing industries. And after that the water will be again treated, and which is nothing but the wastewater treatment, and some of the water will be utilized for agriculture and various recycled water will be used for various application, and then some of the things will be returned to the river. So as we all know, if you want to transport your water from one place to other, definitely we need some device which is nothing but pump. Okay, so I think the mic will be on mute. Okay, if there is necessary I may ask some questions so that you can able to reply. As we all know, pump is nothing but the mechanical device which converts nothing but the mechanical energy into hydraulic energy. So if you are going to give a mechanical energy, it will give the hydraulic energy. And this is the basic definition of pump. Okay. Apart from that, if you want to convey in different form, that is pump can be used to convey the fluid from low level to the high level, and then from low pressure to the high pressure zone, or even from the high level to the low level when the fluid or a liquid is high viscous. So whenever these are the constraints, definitely we need to use a pump. Then only we can able to convey the fluid from one location to the other location. So there are various application. Today is a World Water Day, so that I'm not going to discuss generally only on water, but there are pumps which can be used for various application, because there are many plant engineers who are joined here. So water supply, drainage system, sewage and irrigation system, and then chemical industries, and for petroleum industries for transporting the crude oil, for refineries, and pharmaceutical for mixing the chemical and then transport for various tablets and medicine, other application, and even for medical field where a small art pump, which is almost like you can able to see a small axial pump, which is nothing but the pump which is used for art pumping the blood, and then steel mills, construction, mining, and slurry transport. So these are the various applications where we are going to use the pump in different size and different designs and different way it will be used, operated. Okay. So now I'll just move on to the classification, which is nothing but the grouping of pump. In general, pump will be classified as a displacement pump and then rotodynamic pump. So displacement pump, so normally it is divided into two categories. One is reciprocating and then rotary. So rotary pump will be a piston, plunger, or diaphragm. In rotary, there are various things you can able to see: the vane, piston, screw, flexible members, gear, and lobe pump. So today my topic will be fixed towards the rotodynamic pump. That too in rotodynamic pump, there will be again two categories. One is centrifugal and special effect. We are going to discuss about on the centrifugal pump, which is nothing but the axial flow pump and mixed and radial flow pump. I'll just discuss how the pumps are classified. So based on there is certain things which we can able to classify the pumps. So I just want the audience, how will in general how the pump will be classified or how it will be specified. So I want the moderator just make the mic on, so that I need a response from the, what are the specification is needed for the pump.
Rating
Yeah, rating. Okay.
and think
So
is by rating also.
yeah, can you able to clarify what you mean by
So
rating?
rating means capacity of pump, the pumping capacity.
Okay, pumping capacity. And then Dr. Murugesan has told head record. Okay, fluid properties. And then any other? Yeah, these are the basic three parameters are there, which is there for a pump if you want to buy in the market. So as we are told,
Type of
rating.
pump.
Huh?
Types.
Yeah,
Types.
types. Okay, types. Okay. Okay, I think you have covered the some of the things. Okay, so we will discuss in coming slides. Okay, now this is nothing but the specific speed. So you can able to see a equation. N stands for the specific speed, which is nothing but the function of N is nothing but the rotating speed of the impeller, and Q is nothing but the flow rate, and head is nothing but the total head or head developed by the pump. So specific speed is a function of three parameter. If you want to specify a pump, we need to know this three parameter. Then only we can able to classify the pump based on the specific speed. So you can able to see this chart. So from left hand, you can able to see. So there are two things. One is US unit and metric. For metric, the parameters which is used will be in terms of RPM, meter cube per hour, and head. For US unit, it will be RPM, liter per second, and meter. So depending upon this unit, the values will vary. So 500 till 15,000 and 20,000 and so on. So now if you look at this, so can you able to see my presentation?
Yes, please go ahead, sir.
Okay, okay. Just a minute. So yeah, okay. So if you look at this, US unit is 500. So 500 means which is nothing but specific speed is very less and 20,000 is the maximum. So based on this, what we can infer is when you need a pump for high head and low discharge, then which comes under the category of radial flow pump. When you need more discharge and less head, then we'll go for the axial flow pump. So axial flow pump is almost like a propeller type, and in between is nothing but the mixed flow pump and then Francis Vane turbine. Okay, so this is how the pump will be classified based upon the specific speed. Okay, now I will move on to the different cut section or model which I have taken from the standard APA standard. So single section, double section. So based on this, you can able to understand, some of you there in the plant engineers. So single section and double section, based on that we can able to understand whenever you record more flow rate, then we'll go for the double section. As far as this is concerned, the head developed by any one impeller will be the same. And here, if you need more discharge, then we'll go for the double section. And this is nothing but the closed coupled, or it's a monoblock pump. Normally, these are the pumps which will be used for domestic application. Normally, we used to call monoblock pump. And this is nothing but the pump and the motor are separated together, and then it will be clubbed with the help of coupling, and then with the help of flexible coupling. And this is the vertical mounted end section pump, and then vertical inline pump. So if you look at this configuration, we can able to see some impeller will be axis will be horizontal, some pump will be on vertical. So again, if I move on to the next slide also, you can see the various classification. So double section pump, Again, if we need more discharge, we can go for double section pump, axial split volute. The volute can be splitted from the off, and this is nothing but the vertical pump with the multi-stage. And then this is again different types of pump related to turbine type and axial flow pumps and so on. So I have made some diagrams from the standards which gives information that so basic mechanism or operating procedure principle will be same for all the cases, but depending upon the application we need to choose the right pump and right specification we need to choose. That is the inference we are getting from these standards. Okay, now we'll move on to the what are the basic components there which are there in the pump. So as we all know, impeller is the main heart, and then casing, shaft, bearing, seal, wear ring, and then many nut and bolts will be there, and then many keys and many other components will be there. So I want again the audience to tell. So can you tell any critical components in the pump? Any one critical components based on your understanding. I'm not telling that you are going what you said is right or wrong, but I need input from your participant. What are the critical components for the pump based on your understanding? Bearing and impeller from Dr. Murugesan, sir. Yeah, okay. And impeller, okay, fine. K7, okay. Okay, bearing, impeller, okay. Any other? Seal, okay. So yeah, seal important. Okay, so now I'll stop with this and then I'll move on. So if you look at your drive, okay, drive is also important, and then seal, many people are giving impeller, bearing, seal, and so on. Okay, so whatever you said is all the things are necessary, because everything works together, then only we can able to get the required hydraulic head, even the casing, because without casing we can't able to convert the kinetic energy into pressure energy. Okay, now if you look at the seal, because the pump is a rotating device, so casing will be a stationary and impeller will be rotating. Definitely there will be a leakage will be there whenever there is a stationary and moving component. So in order to avoid the leakage, definitely we need to have the proper sealing. Nowadays we are having many technologies so there to improvise, to reduce the leakage from the sealing. Mechanical seals are there. So now today's a world water day, so with the help of seal we can have even every count of water which we can able to stop from the pump, it can able to conserve for the future generation. Okay, so seal plays a vital role to prevent the leakage from the pump. Okay, so now we'll move on to the pump characteristics. So I think most of the people are from various backgrounds, some are from the plant engineers. I'll just have a look of pumping system or a typical pumping system. You can able to see this is the pump of different types. It may be axial or a mixed or a radial flow pump. So this is a suction line, and this will be the delivery line. And we all know head, total head is nothing but the head developed by the pump. So if you want to be specific, total head is nothing but the summation of, which is nothing but the energy at the outlet minus energy at the inlet. So what do you mean by called as energy is nothing but the summation of kinetic head, potential head, and then pressure head. So this three term is nothing but pressure, kinetic, pressure head, kinetic head, and datum head. This three composite is nothing but the energy. If I'm going to subtract the exit, that is output energy minus inlet energy, is nothing but the head developed by the pump. And you can able to see what is mean by the static head, HS, HD, and so on. Okay, I'm not going in depth because we have only the limited time. I'll just brush up what are the topics to be covered. So this is the generic characteristics of a pump. So if you want to draw a characteristics of a pump, it should be drawn at constant speed. That is a basic condition. So here you can able to see the x-axis will be the discharge and y-axis will be the head. And this is nothing but the total head developed by the pump. And this is the specific efficiency, and this is the coupling power. So now you have the characteristics of the pump. Now if you want to find out the operating condition, so what we need to know? So again, I need an answer from the audience. So now this is the characteristics of any pump. It may be a radial, axial, or mixed. Okay. So now whatever I have drawn is related to radial flow pump. If I want to find out the operating point where the pump is operating, how we can able to tell? So I need a response from the participants. You can text a message in the message. So how to get the operating point? Yeah, intersection between the curve, volume and pressure. Okay. Okay, pump curve. Okay. Yeah, Dr. Dhanasegaran. Okay, fine. So any other from the participants? How to get the operating point? So head and flow. Okay. Okay, so I'll just, I think some of you have given operating point defines at the efficiency curve. Okay, Janganathan. Okay, fine. Okay, I'll just move on to the thing. Okay, now this is the characteristics. Now I'm going to make a system curve. Yeah, you can able to see this is nothing but the system curve. So intersection of total head and then intersection of system curve is nothing but the operating point, which means the pump is going to operate at this point. Okay, so now my next question, okay, I'll just explain. The system curve is nothing but summation of static head and dynamic head. So if you want to, because now I have drawn additional curve. If I want to draw this curve, I need to know certain parameters. One is static head. So static head is nothing but this is the water level. From here, water has to be pumped to this level. So this is nothing but the HZ, which is nothing but the static head. Okay. Apart from that, we can able to see there are various pipelines which is connected between the pumps, suction pipeline and delivery pipelines, and then we have many valves, bend, and other devices will be connected. So which is nothing but the dynamic head. So I will repeat, system curve will be drawn with the help of, which is nothing but the summation of static head and dynamic head. So static head is nothing but the physical elevation from the this surface to this surface, from the sump to the overhead tank. And then dynamic head is nothing but the summation of major and minor losses. As those who are from the mechanical engineering, they may know about the major loss and minor loss. Major loss is related to the friction and minor loss is mainly due to the various fittings which are in the pipeline. If you know that, then we can able to draw this curve and then it will be intersecting. So what I want to tell here is, so now this is the maximum efficiency point. Pump has to run near to the efficiency, but it is running at off the design point. So our aim, we need to move this point towards this point. That is our objective. Okay, I'll just move on so that I'll cover some of the topics. Okay, now we can able to see what you mean by pump in parallel, pump operation parallel. So now I have given the diagram. So I need again, there are two pumps of same specification, pump 1 and pump 2. So this is the Q is nothing but the flow rate, and the flow rate for pump 1 will be Q1 and Q2. The summation will be, definitely it will be added, which is nothing but Q1 plus Q2. So definitely the flow rate in parallel operation will be double. Okay. And what about the head developed by the pump? Whether it remains same or it will be more. So you can just send a text message. So based on this diagram, the pump of same specifications are used in parallel operation. Definitely Q will be more based on this diagram. So Q1 plus Q2. So flow rate will be more. What about the head? Whether head remains same or head will be double. Any answer from the audience? Head develop. Okay, sum of 2. So head develop will be sum of 2. Okay, head remains same. Okay, so I think our moderator is giving almost all the answer. Okay, so I'll just move on. Okay, so here the the specifications remain same, definitely the head will be same for this. So now I have drawn this curve. So again, I'll just explain. X-axis will be the discharge and y-axis will be the head. And this curve is nothing characteristics of any one pump. And since it's a parallel operation, I'm going to add the flow rate, because based on this, I'm going to make this characteristics. This is nothing but the combination of two pump in parallel operation. So by looking at this, you can able to see this single pump can able to develop this much of Q, and double pump means it will be double the flow rate. But in reality, if I'm going to make it in operation in plant, the discharge will not be 2 times. Reason is you can able to see the system curve. As I have told, system curve is nothing but the summation of static head and then dynamic head. So if I'm going to draw this system curve, this is the operating point for one pump, and this is the operating point for a pump, two pump when it is operating in parallel, which means if you look at this Q1 and Q2, definitely Q2 is not twice the Q1. So ideally speaking, we are telling pump in parallel means that 2 times the flow rate, but in reality, it is not the same. So whoever in the plant, they need to be know the reason why we need to go for the parallel operation. Okay, so parallel means summation of flow rate and it will remains the same. But in real case, the head flow rate will not be double. Okay, now we will move on to the pump operation in series. The same pump connected in series. So based on this, you can able to tell. So head developed by the pump 1 will be 10. So here it is 10, both are same, and then definitely the head developed by the pump will be 20. And what about the flow rate? Flow rate remains same because the same Q is going to get from the outside. So the flow rate remains same, but head developed by the 2. So based on the previous analogy from the parallel operation, again, we can say that here the head is twice, but in reality, it won't be same. We can able to see from the characteristic curve. So now this, you can see the below one curve is nothing but for a single pump. So this top one is nothing but the 2 pump in series. So 2 pump means definitely head developed by the pump will be more. Whenever I'm going to draw the system curve, so you can able to see this is the intersection operating point for a single pump. This is the operating point for 2 pump when it is operating in series. Again, you can able to see this is the head develop almost 1000. So based on the ideal case, it should be 2000. But if you look at from this point, it is not near to 2000. So which means in real case, the head develop will not be twice the single pump. So that is the reason whenever we are going for a parallel and series operation, so it is not necessary always we need to go for parallel and series. So in certain case, we need to, instead of going for parallel and series, you can get a new pump of different specification of that Q and H. Then it will satisfy the plant needs instead of going for the parallel and series. Okay, now this is the operating range of your pump. So this is from the standard, you can able to see. So top one is the head curve. This is the net positive suction head related to the cavitation. So in this presentation, I'm not discussing about the cavitation. And this is the power absorbed by the pump. And you can able to see this is the design point. Design point is nothing but the maximum efficiency we are getting. And this is the preferred operating range. This is the allowable operating range. So those who are in the field, those who are operating the pump, definitely the pump has to operate within this range. Reason is you will be getting the better efficiency. Beyond this, there are various losses are there that I will be discussing in next subsequent slide. Why we should not operate the pump more than the preferred operating region or allowable operating region, that we'll see in the next slide. Okay. So now assume that I have the pump characteristics. As I have told, pump characteristics will be drawn for one particular speed. Assume that 1500 RPM. If I know that speed, can I able to get the characteristic at different speed? Yes, it is possible with the help of affinity law. So this law states that so Q is directly proportional to speed, and then head is directly proportional to the square of the RPM, and power will be cubic of speed. So once you know the characteristics of pump for one particular speed, definitely it can be extrapolated for higher RPM as well as for the lower RPM. So no need to do the experiment. Even if you're going to do the experiment at different speed, you will be getting the same trend. There won't be any change. Even there will be minor changes will be there due to losses, but it will be same. So that is the reason with the help of affinity law, we can able to extrapolate or interpolate to get the pump characteristic at different speed. So these are the trend. X-axis will be the speed, and these are the various parameters. So Q and N will be a linear, and then it will be a N square and cubic. Okay, quadratic and then cubic. So this is how the variation will be there if I'm going to change the speed. So based on this affinity law, I can able to construct the ISO efficiency curve. The reason for this ISO efficiency curve is, so I'll just make it N1 efficiency, N2 and N3. That is at different RPM. N1 is nothing but RPM. Maybe assume that 1500. This may be a 3000. This may be a 4000 or something. So different efficiency and different head curve. And based on this, I can able to draw the ISO efficiency curve. So based on the operating range, which I have discussed in the previous slide, so pump has to operate within this region, allowable preferred operating region, then only we can able to get the better efficiency. If I want to run the pump above 85, then this is the zone I need to run. Okay, this is the information we'll be getting from the ISO efficiency curve. Yeah, this is the final, almost we are going to end this presentation. Before that, I'll just discuss what are the various operating conditions of the pump. If I'm going to operate the pump at best efficiency, so I think during the my question, someone has told the maximum efficiency. Yeah, if I'm going to run the pump, operating point is near the best efficiency. That is nothing but the best efficiency point. So operating points and best efficiency coincide, then this will be the best for the operation. If not, if I'm going to run the pump on the higher discharge, the chances of cavitation will be more, because the more the flow rate, definitely the more the velocity. If the more the velocity, so higher the velocity, definitely the pressure will be less. Whenever the pressure, that is local pressure, falls below the vapor pressure, then the cavitation bubbles will be formed. So that is the reason cavitation will be there. And if there is a more flow rate also, definitely there will be more vibration, there will be a more bearing, and the sealing life will be, there will be a problem in the bearing life and seal life. Similarly, if it is less also, there will be a problem. Discharge, recirculation, which are the things, flow phenomena which is taking within the impeller channel. Okay, suction recirculation, reduced impeller life, because assume that in a pipeline, water is flowing and then outlet valve is closed partially. So water has to circulate within the impeller. If it is going to circulate within the impeller, what will happen? Definitely the same water will be repeated again and again. The chances of temperature will be raised, and then because of that, mechanical seal, everything will be damaged, and then this can leads to cavitation and then high temperature rise. So these are the reason this should be avoided. That's the reason we need to operate the pump within the best efficiency zone. Okay, these are the some of the things. I will quickly move on. Okay, so pump operating with the variable speed drive, because in olden days we have the constant speed drive, a synchronous motor, induction motor, so on. So pump will be running at the constant speed, and then we'll be getting the definite Q and H. So nowadays, due to the various technology, we need to operate the pump at different speed. Then only we can able to achieve the required head and discharge. In that case, the only solution is we need to change the speed. So with the help of controlling the voltage or by changing the frequency, we can able to run the pump at different speed. By changing the speed, we can able to get the different characteristics and then operating point. Okay, so this is just some of the case studies I have taken from American Society of Heating, Refrigerating and Air Conditioning Engineers. So in an office building, how the energy is distributed. So if you look at here, you can able to see pumps and fan consume 20% of electricity, and whereas lighting is 23, and other things is almost 10%, whereas pumps and fan consumes around 20%. So from this picture we able to identify that there are more scopes are there in pumps and fan. So if you make a 1 or 2% increase, definitely the energy consumption can be definitely it will be reduced. So this is the information we can able to extract, and this is the general pump life cycle cost. Again, if you look at this, I'll start from the installation life cost will be some percentage, and environmental preparation for making the pump installation will be 5%, on downtime or breakdown times will be a 3%, and energy consumption by the pump will be around 40%, and pump maintenance is 25, pump operation is 10. So if the pump is operating at the right best efficiency, the operation percentage will be 10, but the energy point of view it is 40%. So which means again there are more scopes are there to consume the energy. So how it can be conserved? Definitely the pump should operate at best efficiency point. Okay, so based on this, so it is almost 6:45. I'll just conclude. So based on my thing, I have made the summary like this. A flow in a pump is a complex phenomenon. It depends upon the geometrical features such as impeller, geometry, casing, and section pipe. So if you look at the impeller geometry, so I have shown some cut section. If you want to design an impeller, there are various methods: point by point method, single arc method, double arc method for a radial flow pump. Similarly, if you are going for an axial flow pump, there are aerodynamic method, one-dimensional method are there to have a best impeller profile to get the best output. Similarly, casing is having a definite design procedure are there to get the best geometry. So my point is here, I have designed the pump to the best design. The impeller is designed, and in casing everything is designed for the best operating condition. But whether the pump is operating at the right operating condition, that is intersection of system curve and total head. If it is not going to operate near the maximum efficiency, even though your pump is designed for the best case, so if it is operating off the design point, definitely it does not serve the purpose, which means we need to look for the system head, which means we need to look on the suction pipeline and delivery pipeline such that this point should merge with the best efficiency point. That is the second point. And thus water management can be enhanced by proper design and selection of pump. So if you want to select a pump for any particular application, we need to know where the pump will be used, because there are various applications. If you want to buy a pump for a domestic purpose, we need to know how to calculate the flow rate, how to estimate the total head, then we can able to select the right pump. And for different application, there are temperature is involved and viscosity is involved, and then even the installation. If you have more space, then we can go for a end section pump. If there is a limited space, then we need to go for vertical inline pump. So depending upon the installation constraint, we need to choose the right pump for right application. Okay, so with this slide, I will conclude. So some of the takeaway for research, if anyone is interested to take a research, so they can able to concentrate on design of components, impeller, casing, diffusers, seals, and so on. And then nowadays various open platforms are there. Computational fluid dynamic investigation can be performed to design these components, and then final element analysis mainly to find out the structural strength of the shaft, casing, impeller. And then if you have the facility, you can able to do the experimental investigation, and then through experimental investigation you can able to get the performance and cavitation characteristics. And then nowadays everyone is talking about artificial intelligence, machine learning. So if you know the previous data, that data can be used to get, with the help of AI, we can able to find out what will be the best design for the particular application. And then energy consumption is the main thing. We can able to even a 1 or 2% if you able to save, that makes a difference. And reliability, how long the pump can be used. And finally, sorry, economic consideration. So we need to look out the budget also, because we may think my pump is going to be best, and then I have designed with the help of various tools. But if the cost is more, definitely it does not solve the purpose of the pump user, because for the agriculture purpose, the cost of the pump should be less. Then only they can able to buy, and then they can use it for agriculture. Okay, with this, I will conclude my talk. Thank you. So if there is any questions, you can ask now, or in later days, you can, if there is anything, you can send an email to this email ID. Thank you.